Hello everyone, my name is Pei Zhong. Today I will talk about distribution level markets under high renewable energy penetration. This is a joint work with Xiaojun Lin and Jianwei Huang. As we know, the power grid consists of transmission level and the distribution level. At the transmission level, renewable bid in day-ahead and real-time energy markets, with prices determined by the market. In contrast, for today's distribution level, the renewable generation is either consumed locally or sold to the utility at set prices, which is usually called by net metering or feed-in tariff. Those prices and tariffs are usually decided by a consortium of utility, government regulators, firms, and consumers. Notice that they have conflicting financial interests. Therefore, determining the right prices or charges for distribution level renewable generation has become a fierce political fight. To solve that problem, a possible cure is to build a free market in the distribution level, where renewable producers and consumers can directly trade energy with each other. The hope is that by the invisible hand of a free market, it may be more effective in discovering the right valuation for the renewable energy. In this work, we use solar generation as a typical example of renewable energy that has uncertainty and zero marginal cost. About establishing a distribution level market, most studies focus on real-time energy market just like the transmission level, where they have also shown the price volatility in such real-time markets. However, those works assume that all suppliers cannot withhold the supply quantity. In contrast, our work shows that such withholding will lead to price fixing, which is another severe problem in the real-time market. In order to solve those problems of the real-time markets, we are inspired by other markets that also have zero marginal cost. For example, telecommunication services where people do not use real-time markets. Therefore, we are interested in studying whether other types of distribution level markets can address the pitfalls of real-time energy market. We now give an overview of our contribution. In this work, we first studied the real-time markets. We have shown that uncertain solar generation leads to price volatility, which is similar to other works in the literature. More importantly, we reveal another severe problem, price fixing, that caused by zero marginal cost and inelastic demand in real time. To solve those problems, we then propose a new type rental market that has desirable market outcome under mild conditions. Specifically, such a rental market has zero price volatility. It does not have price fixing. There are some other benefits such as unique outcome and maximized social welfare. We also point out a surprising role of uncertainty in solar generation. In real-time markets, it is a detrimental factor that leads to price volatility. However, in rental markets, it becomes a beneficial factor that induces demand elasticity and a desirable outcome. In this work, we model the distribution level markets as follows. First, there are some firms and each one of them has their own solar panels. We denote the total solar panel size by C, which is equal to the summation of each firm's panel size. We assume that all firms have the same generation efficiency G of T, but we will relax this assumption later. There are also some consumers in this market. Each consumer has her own real-time demand. The total real-time demand is denoted by L of T, which is equal to the summation of all individuals' demand. Besides, there exists a utility as a market operator. The utility can also provide electricity to consumers at retail price pi G. We first study a form of real-time market that is similar to the prior works, where each firm can only vary the bidding price while the supply quantity is always equal to the actual generation amount. The total supply Q of T is exactly the total generation amount. The stacked bidding or supply curve is denoted by the orange curve in the following figure. We then draw the actual real-time demand as a blue curve. Notice that the demand decreases to 0 at the retail price pi g. The intersection then gives the market clearing price pi EQ. Similar to the prior works in the literature, we now show the price volatility in the real-time markets. When there is limited supply, the market price at Nash equilibrium will be driven to the highest price pi g, where every firm bids at the retail price. When there is abundant supply due to the fierce competition among firms, the price will be driven to 0. The last case is a borderline supply. Price will be pi g, where one firm bids at pi g, others bid at 0. We then conclude that such price volatility of real-time markets is mainly due to the uncertain renewable generation. We further advance this line of study by studying withholding and price quantity bids in real-time markets. Here, we report a new problem of price fixing for real-time markets. As we shown in the previous slide, when supply is abundant, firms get 0 revenue, which leads to a strong incentive to withhold supply. If the market allows price quantity bids, then firms may simply lower their bidding quantity. As shown by the following figure, such withholding leads to a new equilibrium with price fixing. That is, the total sum of supply does not exceed the demand at any time, which leads to a fixed market price pi g. Such market outcome is very unfair for the consumers. Notice that in this case, such outcome is not unique because the withholding quantity can be arbitrarily distributed among all firms, so the sold amount of each firm is not predictable. Such a price fixing problem still exists even when a small amount of demand elasticity exists. We use simulations to illustrate the price volatility and price fixing in real-time markets. The x-axis of this figure is time, and the green curve is the solar generation. The magenta curve is the real-time demand. For the single price bid market, the market price is denoted by the blue curve, which is quite volatile. For the price quantity bid market, the price is denoted by the red dashed line, which is always fixed at pi g. Thus, we show that the real-time markets have either price volatility or price fixing. To solve this problem, we then propose a new solar panel rental market. Participants of this rental market trade once over a time period of length t, for example, a month. Note that in this way, price volatility is eliminated by design. Participants of this rental market trade the usage right for a certain size of solar panels. The consumers can use all the electricity generated by the rental solar panels in real time. If not enough, a consumer has to buy the deficit part from the utility at the grid price pi g. We will show that under mild conditions, such a rental market leads to predictable outcome that eliminates price volatility and price fixing, maximize the social welfare, and achieve fairer surplus division between producers and consumers. Now, let me introduce the mechanism of such rental market. Each firm I makes a multi-block bid which contains ki sub-bids. The market stacks all the sub-bids together to compute the supply curve and also collects the demand function from all consumers. The intersection point determines the market price pi EQ. The mechanism of such rental market is very similar to real-time markets, but with a key difference that we now trade panels rather than real-time energy. Due to this critical difference, even though the real-time demand is inelastic, we now see an elastic panel demand function, as we will explain next. To see why the panel demand function becomes elastic, we now present its definition. We first express the time average cost of a consumer N. Cn is the size of rented solar panels. Pi is the market price of renting unit-size solar panels for a unit time. Pi g is the grid price. T is the time period. L is the load. G is the generation efficiency. We can see that the first term is the rental cost, while the second term is the cost to buy the deficit energy in real time. Then the panel demand function is given by the minimizer of such cost. The total demand function will be the sum of each individual's demand function. The demand elasticity is defined by the ratio between the relative change of demand and the relative change of price. An important message is that in such rental market, the uncertainty actually helps to induce demand elasticity. To better understand that, let's see an extreme case. Without uncertainty or randomness, the cost function for consumer will become this. Then we can calculate the demand function explicitly. As we can see, there is almost no demand elasticity when there is no uncertainty. In contrast, when the renewable is more uncertain, demand elasticity will arise, as shown in this proposition. The proposition shows that at any price pi, the demand elasticity is lower bounded by a quantity related to gamma. Here, gamma is determined by the solar generation uncertainty and becomes smaller when the generation is more random. We also use a simulation figure to show this point. The x-axis is the price, y-axis is the total demand function. We adopt 3 different generation amount distribution with parameter sigma, where larger sigma means higher uncertainty. As we can see, when sigma is higher, the demand curve becomes smoother, which means the demand is more elastic. We are now introducing the main results that characterize the outcome of rental markets. We provide this theorem, which says that under a certain condition, the Nash equilibrium must exist, and for any Nash equilibrium, all solar panels are cleared and the market clearing price equals to the inverse demand function of the total panel size. Since all panels are cleared, then there is no withholding. And since the market price is directly determined by the total panel size, then there is no price volatility. We can also find that this outcome is indeed the same as one for competitive markets. The condition of this theorem says that no firm dominates the market, which is close to the reality where the household with rooftop solar panels is a typical firm. This condition is easier to hold when the solar generation is more random, i.e., gamma is smaller. In other words, the uncertainty of solar generation is indeed preferable. To summarize, with mild conditions, the rental market has a unique outcome with desirable features. Here, we use simulation to show that the condition is more likely to hold under high uncertainty. We have already seen the left sub-figure that shows uncertainty promotes the demand elasticity. The right sub-figure is about how easy the condition holds. The x-axis is the penetration ratio. The y-axis is the upper bound of max Ci over C, which is the left side of the condition. As we can see, when the uncertainty is larger, the upper bound is larger, which means such condition is easier to hold. This slide summarizes the benefits of rental market over real-time markets. For the real-time market with single price bids, the main drawback will be the price volatility. For the real-time market with price quantity bids, the price fixing happens due to supply withholding, and thus the surplus division becomes very unfair to consumers. The outcome also becomes less predictable. In contrast, as we have shown, the rental market has no price volatility and have relatively fair surplus division because the outcome is the one for competitive market. The outcome is also unique with mild assumptions, and the social welfare is also maximized if the extra generation amount will be fed back to the grid. This simulation figure is on the social welfare and fairness of surplus division. The x-axis is the penetration ratio. The y-axis is the averaged surplus. The curves in the top shows that the social welfare is maximized in all markets we considered in this work. The curve in the bottom shows that the consumer has zero surplus division in real-time markets with price-quantity bets. The middle curves shows a relative fair surplus division between producers and consumers for rental markets and the real-time markets with single price bids. This figure validates our conclusion that the rental market maximizes the social welfare and achieves fairer surplus division. Readers familiar with markets will see rental market as a form of forward market. At the transmission level, forward energy market, such as day-ahead market, has also been used. Here, we wish to briefly compare rental market with forward energy market. In a forward market, firm I's profit consists of two terms. The first term corresponds to the sold amount in the day-ahead market. The second term denotes the penalty for under-generation in real time. In such a forward market, each firm prefers to bid and clear a lower amount due to penalty. Thus, part of generation is wasted in the day-ahead market. Such problem is not easy to avoid because it might need another real-time market. However, such real-time market could lead to price volatility or price fixing. In our paper, we show an example where the forward energy markets lead to lower usage solar generation than rental markets. So we believe rental market could be a better choice. Please see our paper for details. As we recall, we made the simplifying assumption that all firms have the same generation efficiency G of T. This assumption can be problematic because some solar panels are inefficient, or some firms use part of solar generation for its own demand first. All those factors could lead to a different generation efficiency. Here, we explain a way to deal with heterogeneous generation efficiency. The utility can pull the generations of all panels together and calculate a common efficiency which is equal to the total generation amount over sum of declared panel size. Then consumers are credited by this common efficiency. Thus, consumers do not need to worry about from which firm she rented panels. Then the utility calculates an effective panel size CI for each firm based on historical generation contributed to the common pool. This process allows lower generation efficiency to be penalized through lower effective panel size. Here is a conclusion. We studied different forms of distribution level energy markets under high renewable energy penetration. We show the real-time markets might not be a good choice due to price volatility or price fixing. Instead, we have proposed a new rental market that can be a better choice that eliminates both price volatility and price fixing, and still achieves efficiency and fair outcome. Our analysis also reveals an important impact of solar generation uncertainty on the desirable market outcome. There are many exciting directions for future work. First, we may study the setting where both consumers and producers are strategic. We may also study how energy storage will change the market operation and the outcome. And we can investigate the case where the probability distribution of each consumer's consumption might also be uncertain. That's the end of my talk. For more details, please see our paper. Thank you, and I'm happy to answer any questions.